Hello, HSC 110, Medical Terminology and Body Systems. This is Dr. Teresa, and in this video, we are going to learn about the nervous system. This is chapter 7 in your book. I will say that the nervous system is one of my favorite systems. Of course, I have many, but this can get thick, this information. I feel like the language can get thick if you're not understanding. So I do feel that having that a little bit of the foundation that we've created in this class, or maybe in other classes that you have regarding the language of the nervous system, will be helpful. So chapter 7 starts on page 205 in your book. We're going to go through some of the highlights and things that are important to know about this system. So within the nervous system, we do have to understand that you have two primary divisions. You have the central nervous system, which is comprised of the brain and the spine. And then you have the peripheral nervous system, which is everything outside of the spine. The word peripheral should allow you to extrapolate that that's on the outside somewhere, or, on the fringe, on the border, on the boundary. The peripheral nervous system will include spinal nerves, cranial nerves, and sensory receptors. One thing I like to impress upon students is I feel like we have been taught that the nervous system, the only thing it does is, tell us when we have pain. That is one of the smallest functions of the nervous system. Only about 10% of the entire nervous system is responsible for detecting pain. It does many other things as far as stimulus detection, or bringing in information to the body, understanding what it is. But most of the nervous system is off dictating what the body's going to do. So pain is a very, very, very small portion of what the body's up to. Now, when we talk central nervous system and peripheral nervous system, this is how we divide it to talk about it structurally. Again, central nervous system, brain and spine. Peripheral nervous system, everything outside of that. Spinal nerves, cranial nerves, sensory receptors, everywhere else in the body. But then we break it down into what's called a functional division. And this is afferent nerves and efferent nerves. Now, the difference being afferent nerves are going to bring information into the central nervous system. The efferent nerves will take information or deliver direction to the body from the nervous system, central nervous system. So there's a little acronym that may be helpful in understanding this, which I will give you in a second. But with those afferent nerves, again, afferent nerves are going to pull sensory information into the central nervous system, into the brain and spine. Okay, sensory, if we think about that, you're able to sense things, to know that it's there. In order to know that it's there, your body has to be able to bring that information into your central nervous system so that it can effectively then tell your body what to do about it. Within this division of sensory afferent nerves, you have something called a somatic sensory nerve fiber. Anytime you see the word somatic, that's going to tell you it's going to be related more towards the outside of the body, or the body wall, we could say. Anytime we hear the word visceral, and I believe I mentioned this probably in our very first lecture, visceral sensory fibers, that's our guts, okay? Anything that, like our organ systems. So these afferent nerves will bring information from the wall of the body or the musculoskeletal system, as well as from the organ systems, take the information of what's going on in these regions and take signals to the brain and the spine. When we talk about efferent nerves, then, these are what we call a motor nerve, okay? Think about it, a motor goes into action, right? Or can make action happen. So a motor nerve that is efferent is taking or transmitting a signal from the central nervous system, from brain and spine, and taking it to the rest of the body. Now that can be either to the body wall or to the organ systems. So within the efferent nerve classification category, we have the somatic nervous system. Again, that's like your muscle, bone, and joint stuff. Or the autonomic nervous system, which is, when we use the term autonomic, it's automatic. It goes and does its own thing. So the acronym that you may find helpful to be able to do this, let's see if I can do this. Sensory, afferent, and motor efferent. Makes the word same. So when we're talking functional divisions, I use the acronym SAME, S-A-M-E. S is for sensory. A is for afferent. Again, bringing in, it senses information and brings it into the central nervous system. Motor efferent. Motor, something's going to be activated or directed or dictated. Efferent, the central nervous system tells the body what to do. This is a great picture that you can use to look over. Basically, it's saying what I just said, but takes it a step further. So this is on page 207 in your textbook, and I think it's really helpful to have these. Okay, so you can see in the yellowish box, it's labeled the central nervous system. You can see then the red line that goes to the peripheral nervous system. That's our motor efferent nerve. Again, it takes information or signals and transmits them away from central nervous system and tells the rest of the body what to do. Within the PNS, or peripheral nervous system, which is everything outside the brain and spine, it will take information from sensory receptors and deliver it to the central nervous system. Within the PNS, okay, there have to be sensory receptors in it so that it can send information to the central nervous system. But the PNS is then divided into the autonomic, which is automatic. Okay, this is your organ systems, things you don't think about, involuntary things, but also to the somatic nervous system or skeletal muscles. Again, somatic tells us body wall structure, muscle, bone, joint stuff. Within the autonomic division, and this is one of my absolute favorite parts of the nervous system, how it works, we have the parasympathetic nervous system. This is your wine and dine response, and also can be part of the sexual response. The parasympathetic nervous system is really where you get to heal and downregulate anything of high stress. The sympathetic nervous system, that's your fight or flight response. If you're in high fight or flight, you will not urinate well, you will not digest well. The sexual response may be impeded. Your immune system doesn't work well. So we see fight or flight responses under times of high stress. This is real or imagined stress. It doesn't have to be in the present time. Okay, this can be activated by thoughts and emotions. It does not have to be a real threat. And that's relevant and evident when we hit into like anxiety and PTSD, that it's just a thought, it's just a worry. It's not even in real time or present time. And then we get activated into this response system, which by then, if this is hypertoned and the parasympathetic nervous system does not get to function well, your parasympathetic nervous system, again, this is where you digest food. This is where you feel safe and relaxed, chilled out, you digest, you urinate, your immune system function works well, you sleep well. Can you see how times of high stress will impede pretty much everything that your body does, that needs to do on the regular? Okay, it's gonna deliver you a non-healing tone or an inability to heal. Okay, when we talk about the actual composition of the nervous system, we have to look at the cells of the nervous system. We likely have all heard that neurons are the cells of the nervous system, but there are other supporting cells that we will mention that are super relevant as well. The neuron is what is responsible for transmitting the information that we've talked about, the stimulus, or how does it get, from your fingers to your brain? Well, it is by way of these specialized cells. Now, when we have a cell, the cell body is called the soma or the neurosoma. These will have projections off of them in varying shapes and forms. But this kind of reminds me of the hairdo of like Marjorie Simpson, just by way of, we have this, the soma or the neurosoma, okay, and then we have these projections off. Now, these projections that come directly off the soma or the neurosoma are called dendrites, and these guys will be the receivers of a stimuli from either directly or from another neuron or another cell or something that's delivering it some information. Within the neurosoma, we see it does have a cell body it does have a nucleus. Off of this neuron, we have this area here, okay? And then it looks like it has a big long tail. That big long tail on the neuron is called an axon. Some of the axons of neurons will be myelinated, okay? Those are these little looks like bubble wrap the whole way along the axon. Now, what this helps with is electrical conductivity and kind of keep the signal transmitted within a tube. If you know anything about like wiring in your house, it's the same thing. It's the same construct with insulated wires. Okay, so Schwann cells will insulate the neurological impulses that are conducted along this tail of the neuron. These specific myelinated axons are created from what's called a Schwann cell. In between each Schwann cell, we have a little cleft called the node of Ranvier. This also will help with the speed of the conduction. Now here you get a better picture of that Schwann cell. Okay, it's a different kind of cell that wraps around this axon, does have a nucleus, okay, and it produces what's called the myelin sheath. Okay, also has a part to it called the neurolemma. And I'm going to get into a little bit better the definition of some of these parts. At the end of the axon, we have these little things, look like little bulbs. Okay, these are called axon terminals. The axon terminals are going to synapse or connect with either another cell or another type of tissue, delivering it some function. In this case right here in this picture, this first neuron we're looking at, this would be called the presynaptic neuron, where the axon terminals connect with the next neuron, Okay, again, they synapse, and this would be a post-synaptic neuron. Okay, so the cell body of a neuron will include a nucleus, mitochondria, and other organelles. However, centrioles are not present because most neurons are not capable of replication. Let's say most. We talked about dendrites. Those are the guys that will pull the stimulus into the cell or the previous impulse or synaptic chemicals or neurotransmitters. At that synapse, or the location where the two neurons are meeting, that is generally where there is the release of neurotransmitters between those axon terminals and the secondary neuron. I mentioned that there is a synaptic cleft. So between the axon terminal and that next cell, there is a space, and it is within that space where the neurotransmitters or chemicals from the cell that are being released, they get released into the cleft. And then that second neuron, or the postsynaptic neuron, will have receptors for a particular neurotransmitter or chemical, and they pick them up, and then they receive a message and do their particular job. When we classify neurons, there are three primary functional types of neurons. We have a sensory neuron. This will carry impulses from the skin and from organs to the spinal cord and brain. I mentioned that previously. Then we have a motor neuron, the efferents. These neurons will transmit impulses from the brain and the spinal cord to muscles and glands, directing body actions. Interneurons, or what we call association neurons, these will form bridges to transmit impulses to other neurons. So sometimes there's like that in-between neuron. That's the interneuron. It's like a relay. Now we have different, I mentioned this, okay, different structures of a neuron, and their structure will help determine their function, and their function can help determine what needs to be there. So in a bipolar neuron, they have one axon and one dendrite. Now, when we say that, okay, that just means the whole extension coming off of one end of the neurosoma, okay? At the end of the dendrite, you have dendritic branches, which will sort of spread out like little tree branches, okay, picking up different signals and stimuli. And we saw that within the axon terminal as well. They have like these little tree branches at their ends. A unipolar neuron, these have a single axon with processes that extend in opposite directions. They have dendrites on the peripheral end and axon terminals on the central end. The peripheral process carries impulses to the cell body, while the central process will carry impulses to the central nervous system. When we talk multipolar neuron, these have one axon and multiple dendrites. All motor neurons and interneurons are multipolar. The neuroglia, also known as glial cells, are specialized cells that are for support functions. And I mentioned these like 2 slides up. Okay, so these are really relevant within the central nervous system, and it's going to be slightly different between CNS and PNS. Within the central nervous system, we're going to find cells that are called astrocytes. So astro should tell us they kind of look like stars when we see that prefix. So they link capillaries within the CNS to specific neurons. Hopefully that makes sense, right? We need some kind of way to deliver nutrient exchange with these cells and for their own health. Astrocytes account for nearly half of all neural tissue. Then we have something called a microglia. That is right here, these little yellow things on this picture. By the way, I'm on page 210 in your book. The microglia will absorb and dispose of the dead cells and bacteria. So they have a macrophage type activity, or like, macrophages go around like little Pac-Man and eat things. They eat debris or whatever doesn't belong there. Then we have right here, okay, these are called ependymal cells. They will line a canal or cavity. They will serve to form a bit of a protective covering. Yeah, that's all we'll say about that. Okay, so then we have the oligodendrocytes here. The oligodendrocytes within the central nervous system will be the producers of myelin. We mentioned myelin in a few slides previous when we were talking about Schwann cells, and Schwann cells are specific to the peripheral nervous system. So then when we get into the PNS, we have two types of cells there that we want to talk about. These are satellite cells. They serve as a cushion for neurons. And then we mentioned the Schwann cells again. So we have oligodendrocytes within the central nervous system that are responsible for producing the myelin around the axon of the neuron. Within the PNS, the Schwann cells are responsible for the production of the myelin sheath. So for your first section that we just went through in chapter 7, just to review some of the language again, we had afferent nerves. Afferent nerves are sensory and send impulses from receptors in the skin, the muscles, and the joints to the central nervous system. The efferent nerves, these are motor transmitters that carry impulses from the central nervous system to the muscles and glands, as we have mentioned. The autonomic nervous system is the branch of the nervous system that will control involuntary body functions. We have the central nervous system, which we mentioned repeatedly. That is the division of the central nervous system that includes brain and spine. The peripheral nervous system includes all the parts outside of the brain and spine, whether it's spinal nerves, cranial nerves, or sensory receptors on the periphery. Now, in contrast then to the autonomic nervous system, we have the somatic nervous system. This is a branch of the nervous system that will stimulate skeletal muscles. When we're talking the cells of the nervous system, we have the cell body, or the soma, or the neurosoma. We learned about the dendrites, which pick up the sensory information. We have an axon, which is the little tail off of the neuron that will deliver, transmit the electrical impulse to the next cell or tissue. We had the myelin sheath within the central nervous system. The oligodendrocytes are the producers of the myelin sheath. In the peripheral nervous system, the Schwann cells are responsible for that. The nodes of Ranvier that we saw on those pictures, these are the little gaps within the myelin sheath where the axon is exposed. The neurolemma, we mentioned that on the one picture where the myelin sheath was noted. This is a thin membranous sheath that envelops the nerve fiber. We learned about a synapse. Okay, a synapse is the intersection between two neurons or between a neuron and a muscle or gland or whatever's next in line. And the cleft is the space or the gap at this area. We learned about the neuroglia or the supporting cells within the central nervous system as well as the peripheral nervous system. So then, as we learn how the electrical conduction actually works, if you can kind of take your head back to like that section on chemistry, that'll be important because we have to review some of that. That is why your nervous system operates electrically as well as your heart. So this is relevant for all cell function really, but specifically in these areas. So the neurons will behave kind of like our muscle cells that we learned about. They demonstrate irritability, meaning they respond to a stimulus. And the ability to convert the stimulus into a nerve impulse. They have the ability of conductivity, meaning they can transmit it or send it to the next guy down the line. A nerve impulse, also when we're talking about this is the electrical nature of it. If you know anything about electricity, it's really the physics of the chemistry. Okay, so it's the charges, the charge differences, super and highly relevant in how your body operates. So when a neuron is inactive or at rest, there are potassium ions inside the cell and sodium ions outside the cell. Although both ions will have a positive charge, due to the concentration from one side of the cell to the other, there's going to be a difference. What it's going to do is make one side of the cell membrane more negative and or more positive than the other side. So the inside of a cell will be more negatively charged than the outside due to the concentration of these positive ions. Because of this difference, the cell membrane is said to be polarized. This will be super relevant in understanding this. Anything that's polar or in polarity is opposite. So this is everything everywhere. Okay, this can be negative charge, positive charge. This can be dark, light, day, night. This can be male, female, masculine, feminine. This can be North Pole, South Pole. The electrical potential associated with this polarized state is known as the resting membrane potential. And there are many different stimuli that can activate a neuron. A bright light in the eyes, a bitter taste on the tongue, or the reception of neurotransmitter chemicals from another neuron are all possible stimuli. But most of the time, okay, we have a neurotransmitter from a presynaptic neuron. We can have a weak stimulus trigger a change in the cell membrane in like one point, one little spot on a neuron. And this can happen all over the neuron, okay? So, I mean, not every stimulus, what we're saying here is not every stimulus that is applied to a neuron is going to instate an action potential to change or for a depolarization principle to change. So let's get into what that means. So I think Now you have an awareness of what polarity is, or what it means to have a neuron in a polarized state. That means that we have a charge difference from one side of the membrane to the other. Anytime you see the word depolarized, we're bringing something out of this vast difference of charge in this case, and we're bringing it toward a more neutral or even past neutral into a completely different state. So we're changing then the charge from one side of that membrane to the other, bringing it into a more neutral. Anytime, by the way, we have something that is polarized, that is so vastly different like that, anytime, it delivers us the ability to do work. When we have then the charge across that membrane come into more neutral via depolarization, there is energy exchanged or released or created. If there's energy involved, there's work that can be done. So there's what we're doing in this case in a neuron is we're taking the energy created through depolarization principle, and we're taking it from one form and converting it into like an electrical energy and sending it down the rest of the axon. Now, it can have multiple little local triggers, okay? If it doesn't reach a particular threshold within the neuron, it won't send the electrical impulse down the rest of the cell. Within a few milliseconds, following the discharge of an action potential, the membrane becomes impermeable to sodium ions, but permeable to potassium ions, which will then rapidly diffuse out. This begins the process of restoring the membrane to its original polarized resting state, and we call this repolarization. So after depolarization, and after we have this energy release or electrical transmission sent down or whatever happened from that energetic exchange, we have the cell is going to want to repolarize itself so that it is available to do work again. Until the cell membrane is repolarized, it can't do anything with more stimulus though, because there's the difference in charge across that membrane has been taken away. Therefore, the ability to send a signal or do any work has been taken away until it reinstates itself. So this little space of time between depolarization and repolarization is what we call the refractory period. So nothing's getting done. It's fatigued, it's kind of taking a break, it's at rest. So following repolarization, the membrane is restored to its initial state. This occurs through the activation of the sodium-potassium pump. And I believe we talked about that likely in chapter 2 in the chemistry section. Okay, sodium-potassium pump delivers us the knowing that sodium in the body is required. It's in every cell to reinstate a cell to its resting membrane potential, so it has the ability to go into action if required. And what it does is it reinstates polarity. It's going to push more sodium out of the cell than it has potassium in the cell. When we talk transmission speed, some things that are going to impact that. The presence or the absence of the myelin sheath will have a play in this, as well as the diameter of the axon. The sheath, again, is the electrical insulator. The action potentials within a myelinated axon will jump over the myelinated regions of the axon. The depolarization only will occur at those nodes of Ranvier then. This process is known as saltatory conduction and will result in faster impulses. If it's a non-myelinated axon, and that's relevant to understand, not all axons will have a myelin sheath around them. Thereby, they will have slower transmission speeds. But if those non-myelinated axons have larger diameters, that will help them. The larger the axon, the greater the number of ions there are to conduct current. There's a third factor that will influence the transmission speed, and this has to do with temperature. Warmer temperatures will increase ion diffusion rates, whereas local cooling, which occurs when holding an ice cube or an ice pack on something, will decrease the ion diffusion rates. And that's just kind of, again, going back to that section on chemistry, understanding a little bit better about what diffusion is and does. If you don't recall, diffusion is particle movement across that membrane. We say particle, we say ion in this case. And there are certain factors that just always inherently are going to impact diffusion, and one of them will be temperature. So the type and size of the nerve axon also has a lot to do with the speed of its conduction. Impulses that signal limb position to the brain will travel extremely fast. Information or impulses from the objects people touch travel more slowly. The sensation of pain moves even more slowly. Thought signals, which are happening as you're like anything, right? Anytime you're thinking, they happen around 20 to 30 meters per second. So way faster than pain. Sensation, the sensation of pain, not damage pain. So you're knowing something's there. Neurotransmitters, one of my favorite things. Now, we learned a little bit about neurotransmitters in the muscle section. We were talking about acetylcholine. So again, here is a great picture of the synaptic cleft. We have an axon terminal. We have vesicles of neurotransmitters, which are the chemical packets produced by a neuron. When we're, and this is going to differ, okay? I think we are aware. If you're not, there are different types of neurotransmitters. When we were talking the neuromuscular junction, that is primarily about acetylcholine, but neurotransmitters are fascinating because they will dictate behavior and action. So this means that if you have dopamine, which is a neurotransmitter out of balance, we'll say in deficiency, you might be more prone to addictions and extreme thinking, impulsive behaviors, stuff like that. If you are serotonin deficient, that's going to lead you into depression easier. If you are GABA deficient, that's going to lead you into anxiety situations. So neurotransmitters, one of my favorite things to talk about. We understand the anatomy, we're getting some of the physiology, and then how that's going to lead or dictate our behaviors, like a ginormous deal. So in regards to the neurotransmitters, when an action potential reaches an axon terminal, the terminal will depolarize, come to more neutral. Calcium gates will open, and then calcium ions will flow into the terminal. The influx of calcium will cause these vesicles of neurotransmitters then to join the cell membrane adjacent to the cleft, and then pores will form in the membrane, allowing the neurotransmitter to diffuse into the cleft. Neurotransmitters can have an excitatory effect or inhibitory effect on the receiving cell. It's going to depend on the receptors in the cell, okay? Just because, for example, serotonin's release doesn't mean the postsynaptic cell will be able to receive the message. The final step in communication between nerves out of synapse is the removal then of the neurotransmitter. Usually they can get reabsorbed. Okay, this is also relevant if anyone is on or knows anyone that's on maybe a depression medication and they're on what's called an SSRI, selective serotonin reuptake inhibitor. So that allows, not all of the serotonin to be reabsorbed, so that's still available by the postsynaptic cells and et cetera, et cetera. When we're talking, let me hit this point real quick. On page 213 in your textbook, you can review the little tan section where we talk about nerve conduction studies and aging. I'm not going to read through that. I'll let you read through that on your own if you choose. Okay, when we get into reflexes are very important within the body. And we're all aware of the patellar reflex because we get that checked when we're at the doctor's office and we're looking to make sure a reflex arc is intact. You have visceral reflexes though as well. So reflexes are simple, rapid, involuntary programmed responses to stimuli. They're involuntary. You don't have time to think. So this is like if you touch the hot stove, your body is going to be able to detect tissue damage. Then you'll be able to withdraw your hand without consciously going through the action of thinking it through. It just happens. So this is will involve the transmission of impulses that will follow a specific arc that includes both the peripheral and central nervous system structures. So somatic reflexes are those that involve the stimulation of skeletal muscle. Again, somatic, that tells us body wall, muscle, bone, joint stuff, okay? An autonomic reflex, these are reflexes that will help regulate cardiac muscle as well as smooth muscle. So your heart, maybe your bladder, your stomach, your vessels, we have specific cells placed in specific areas in order to detect either pH changes or pressure changes. So that's going to then stimulate responses within the body that you don't even have to think through. So this could be so that you can regulate your blood pressure when you go from sitting to standing. Okay, so I'm going to do something a little bit different here. Within this section, okay, before we move on to 7.3, I'm going to ask 2 questions. And these will be made into or graded. They'll be made into a little quiz. I may make them into a bonus. I don't know yet. We'll see how everybody does. Okay. So the first question that you have to answer, and again, this will be made within into a little quiz. Please name for me the 2 divisions of the autonomic nervous system. And the second question, what effect does a myelin sheath have on a nerve impulse? Okay, so let's go into then the central nervous system. There's a nice chart on page 216 that helps break down and separate the anatomy. When we're looking at the brain itself, okay, we have to understand the parts of the brain. And there are great pictures on page 217 for this as well. So you can have the same picture on page 217 as we're looking at here in the PowerPoint. So The divisions of the brain, you have the cerebrum, the diencephalon, the brainstem, and then the cerebellum. When we're looking at the cerebrum, okay, that's the biggest part of the brain. Some things we have to understand and note on the brain. We have this giant separation in the hemispheres. Okay, this is called the longitudinal fissure. Then we would have a left hemisphere because we're looking at this kind of obliquely, but this is the posterior aspect. We have something called a lateral sulcus that we'll notice within the cerebrum. And here's this whole half is the right cerebral hemisphere. When we look at lobes, okay, we break the cerebrum up into regions called lobes. They include frontal, temporal, parietal, and occipital. The primary division or divider between frontal lobe and the temporal lobe, or we can say temporal lobe with frontal and parietal, that's that lateral sulcus we pointed out. The primary division between the frontal lobe and the parietal lobe is this marking called a central sulcus. And then between the parietal lobe and the occipital lobe, we have a parieto-occipital sulcus. And then on this picture too, you can see the cerebellum as well as brainstem. Now, let's point out some terminology here as well. I've mentioned the word sulcus multiple times, okay? When we're talking a sulcus, this is a groove. And we'll see this in other systems as well. Coronary circulation, we talk about a sulcus. So it's like a groove or something else lies in it potentially. Now the ridges that we see within the cerebral hemispheres, which are called gyri or gyri. We also might see the fissures, okay, like the longitudinal fissure. These are uniformly positioned deep grooves in the brain. We mentioned that longitudinal fissure will divide the brain into left and right hemispheres. And they're connected by what's called the corpus callosum, which is a large myelinated tract that connects the hemispheres. The neural communications to and from the right side of the body are controlled by the left brain, and communications with the left side controlled by the right brain, which I think we knew that. The frontal lobes, okay, the frontal lobe of our brain, this is our forehead. The anterior association cortex is located on the most anterior portion of the frontal lobe and plays a high role in our intellectual functioning. This is why we think we're higher order animals. So we can plan and reason and have memory. The left frontal lobe also includes what's called Broca's area. Broca's area will control the tongue and lips for speech and for movement during speech. So if we have damages in this area, this will contribute to difficulty speaking, like if we have a stroke, or even like in Alzheimer's patients, if the beta amyloid plaques take over this area, that can happen. Within the frontal lobes, just anterior to the central sulcus, we have something called the primary motor cortex. This structure will send neural impulses to the skeletal muscles to initiate and control the development of muscle tension and the movement of body parts. Axons that descend from the neurons in the primary motor cortex will join to form what's called a pyramidal tract. This will communicate with the brainstem and the spinal cord. The parietal lobes are posterior to the frontal, and they include the primary somatic sensory cortex, which will interpret sensory impulses received from the skin, internal organs, muscles, and joints. The somatic sensory cortex illustration represents the density or amount of sensory neural input received from different parts of the body. The occipital lobes, these guys are responsible for vision or interpretation of vision. They include the primary visual area where the inputs are received, and then the visual association area where the inputs are interpreted. Within the temporal lobes will include the primary olfactory area, which I think we can extrapolate. That's responsible for our smell. The primary auditory area for hearing. The auditory association area where the signals get processed, and then something called Wernicke's area, which helps interpret speech. So Broca's helps us with actual speaking. Wernicke's helps us interpret what we hear. So it's the processing center. Okay, let's look at this. Okay, so we mentioned the motor and somatic sensory cortices. Okay, so the primary motor cortex, which is what we're looking at, this on page 219, and also the slide we're looking at in front of us on the left side of the slide as we're looking at it. The primary motor cortex sits right in front of that central sulcus line that we pointed out. You can find the central sulcus on this picture. Okay, right down the center here. Here's the sulcus, central sulcus. Right on this pre-central gyrus is what we're talking about. So here, this portion of the brain, we understand that it's motor. Okay, so this is where actions will sort of, after interpretation, will be dictated from this space. Now, this is called a homunculus. It's a weird map. You can see on it, it looks like the hands are big and the feet are pretty big and the lips are big. Okay, so think about that. What we're saying happens at this part of the brain is that there are actions directed here, and it's going to have a large portion of coordination of the feet and the hands for whatever kind of movement they're going to do, and a lot to do with the face, maybe expressions as well as speaking. Okay. Now, right behind them, that central sulcus, we have the gyrus behind that guy. This is our primary somatic sensory cortex. So we're bringing information into this area from somatic regions in our body. Remember, somatic, body wall, muscle, bone, joint stuff. Okay, and again, you can look at the distribution of how the body will pull sensory information from the body into this area. So we see that, again, lips and face, pretty big deal. Hands are pretty big. Genitals, okay. The tongue, some of the intra-abdominal workings will be pulled in here. When we talk diencephalon, the diencephalon, okay, we don't have a great picture here on slide, but it's on page 219 because the diencephalon is kind of like tucked up in between everything. This is known as the interbrain. It's located deep inside the brain, enclosed by the cerebral hemispheres. It will include the thalamus, the hypothalamus, and the epithalamus. The thalamus is the relay station for communicating both sensory and motor information in the body and in the cerebral cortex. It deals with arousal, sleep, wakefulness, and high alert consciousness. The hypothalamus, which is about the size of a pearl, is huge in autonomic nervous system regulation. It has a lot to do with heart rate, blood pressure, thirst, hunger, energy, body temperature, hormone production centers. Okay, this is where things get dictated and regulated. The epithalamus includes the pineal gland. Pineal gland is a magical little thing that we don't know everything about, by the way. It has a lot to do with hormone secretion, melatonin production, which would then thereby deliver us our sleep cycles. The brain stem, which is about the size of our thumb then, is shaped like a stem and includes three structures: the midbrain, the pons, and the medulla oblongata. The midbrain is the superior end of the brain stem and is the relay station for sensory and motor impulses, and specifically relays information concerning vision, hearing, sleep, arousal, temperature, all of that stuff. The pons is right below that and regulates or plays a big role in breathing regulation. The medulla, which is then inferior to the pons, helps regulate heart rate and blood pressure and breathing, and will control reflexes for coughing, sneezing, and vomiting. We also have something called a reticular formation. This is the collection of integrated gray matter that extends the length of the brain stem. It's a group of neurons within the reticular formation known as the reticular activating system. It's involved in regulating states of wake, our cycles, okay, our rhythms, waking, sleeping, and awareness. Damage to the system can result in coma. So this could come from severe brainstem injuries or brain injuries in general. One thing I didn't mention that I want to, let me go back here and see if I have a picture of it. Okay, we've heard of, white and gray matter in the brain. Okay, white matter is myelinated, gray matter isn't, within the brain itself. Okay, the cortex of the brain, or the outermost portion, is gray matter. And then different structures within the brain. Most of the inner part of the brain is going to be white, but not all of it. Okay, when we're in the spinal cord, it's opposite. The cortex of the spinal cord is white matter, and then the gray matter is on the innermost portion of the spinal cord. Okay, there's a neat box on memory on page 220. Again, I'm not going to read through that for you, but understanding really how memory takes place, it's quite complex. There are different structures involved, one of them being the hippocampus. Okay. So I mentioned the diencephalon. I'm sorry, our pictures here. I walked through all of this. Okay. We talked about the reticular activating system. There's another tan box, page 221, where it talks about stroke and mini strokes or transient ischemic attacks. We're going to talk through the cerebellum now. The cerebellum is the smaller part of your brain that kind of sits underneath that occipital lobe of the cerebrum. It looks similar to the cerebrum with its outer gray cortex, with its convolutions and dual hemispheres. It has an important role in regulating the body movements as well as coordinating balance. It will receive input from eyes and ears and sensory receptors from all over the body, telling it what, like proprioception, okay, it's awareness of itself. Now, meninges, really cool. These are the membranes that will surround everything. So the meninges of the central nervous system we'll see in 3 layers. The dura mater, which is the outermost layer, the inner layer between the sandwich, or the inner part of the sandwich, is called the arachnoid mater. And it's called that because it will have these little extensions that will anchor into what's called the pia mater. Pia mater is the layer of connective tissue that's right up against the brain matter. We can see within this picture, and there's a picture on page 223 in your book as well, okay? We get to see how the layers of the meninges sandwich together and line up. You can see the extensions of the arachnoid mater going into the pia mater. You can see the subarachnoid space. That should tell you that it's a space underneath the arachnoid mater. You can see the dura mater, which comes in contact directly with the skull, if we're talking surrounding the brain. We hear a lot also about the blood-brain barrier and how certain things can cross it and certain things can't. If you have compromised integrity to this barrier, things will get into your nervous system that you don't want to. And I don't think this is hard to compromise the integrity of, actually. This does serve as a protective mechanism so that we don't have weird pH changes or damage to the nervous system tissue itself. Okay, spinal cord extends from the brain stem to the beginning of the lumbar region of the spine. So let's walk through then the parts of the spinal cord. You can see first off, the layers of the meninges, they're going to be the same as in the brain. You have the dura mater, which is the most external layer, then the arachnoid mater, which will anchor into the pia mater, which is right up against the spinal cord. I mentioned that the spinal cord has its gray matter on the central portion and the white matter in the cortical portion. Now, on the posterior aspects of the spinal cord, this is where sensory information is going to come into the white matter. When we're talking white matter, we label it by talking about columns. Okay, so the posterior columns of the white matter, we're going to take or receive information, sensory stimulus, take it up to the brain. Okay, the lateral and anterior columns of the spinal cord then will be able to direct or receive and direct information both from sensory stimuli or motor action and direction. When we're talking the gray matter in the central portion of the spinal cord, we section that off in what we call horns. So the gray matter will have posterior horns, lateral horns, depending on what part of the cord you're in, and then anterior horns. Right in the center of the cord, We have the central canal. This is going to be primarily responsible for carrying cerebrospinal fluid. Now, the nerve roots off of the spinal cord, the ones that are on the posterior end, these will be posterior rootlets, okay, or dorsal rootlets. They're going to then commune into what we call a dorsal root. So we have rootlets coming into a root, then they will all commune into what's called a dorsal root ganglion. So that's like a ball of synapses and connection points. After it leaves there, it will commune with ventral roots from the ventral portion. When they combine, they will actually form the spinal nerve. The spinal nerve or what will exit like in between your vertebra and go to a particular part of your body. One thing I did want to mention, I think I said this already when I was talking about white and gray matter in the brain, but white matter is generally myelinated, whereas gray matter is not. And this can also be a point where the gray matter can be like a stronger concentration of cell bodies rather than axons. And they kind of go together, okay? The axons are what are myelinated, so therefore they'll represent high concentrations of white matter. When we have collections more of cell bodies, that's going to be more of the gray matter. Okay, so question on your quiz that I will make will be to give me the 3 layers of the meninges from the exterior layer to the interior layer. Okay, as we go into the peripheral nervous system, we have to talk about what a nerve actually is. A nerve is not an axon. An axon is part of a neuron. So really a nerve is a collection of axon fibers. So this picture is great. You can also see it on page 225. So we have an axon coming off of a neurosoma somewhere, will be wrapped in a myelin sheath, and that myelin sheath will be wrapped in a connective tissue called endoneurium. You'll have multiple axons wrapped in a bundle covered with what we call perineurium. You will have multiple of these collections of axons in a bundle called a fascicle. The fascicle will also be wrapped in perineurium. You will have multiple fascicles encapsulated within connective tissue called epineurium. That is a nerve. Within that epineurium bundle, when you have the multiple fascicles, also in between them, we're going to see blood vessels. Okay, it's relevant to understand that within the peripheral nervous system, we have what are called cranial nerves. Now, these guys are kind of cool because they come right off of brain and spine. Okay, we have 12 pair of them. They will relay impulses to and from the left and right sides of the brain. So they'll have name and number. They'll be numbered 1 through 12, cranial nerves 1 through 12. Each will have a name, and then it will have a particular function. Some of them will be only sensory nerves. Some of them will only be motor nerves, and some of them will be mixed nerves. So we have cranial nerve number 1 is our olfactory nerve. Cranial nerve number 2 is our optic nerve. Both are sensory, by the way, only sensory. They just pull information in. Cranial nerve number 3 is the oculomotor nerve, and this has both functions, both sensory as well as motor. and it is responsible for eye movements. Cranial nerve number 4 is the trochlear nerve. This is both sensory and motor, so it's a mixed motor nerve. Eye movements as well. We have a lot for eye stuff. The trigeminal nerve is cranial nerve number 5. Trigeminal nerve is a mixed nerve, meaning both sensory and motor, and it deals with facial sensation and jaw motion. And then we have cranial nerve number 6, which is the abducens nerves, again, a mixed nerve for eye movements. The facial nerve is cranial nerve number 7, mixed nerve for facial movements and taste. Then we have something called the vestibulocochlear nerve. This is sensory only. It's for hearing and balance. Cranial nerve number 9 is the glossopharyngeal nerve. This is mixed nerve of throat muscles and for tasting. Cranial nerve number 10 is the vagus nerve. This is for the autonomic control of the heart and the lungs, digestion, taste. And this is truly the pathway between your brain and your organs, or your brain and your gut. The accessory nerves, cranial nerve number 11, mostly motor. This is for shoulder movements and neck movements, which ultimately then can move your head. Hypoglossal nerve is mixed. This is for tongue movements as well as sensations. And you have a nice chart for that on page 227 in your book. Then let's talk about spinal nerves. You have 31 pairs of spinal nerves, which will come off of the cord in pairs. So you have to remember your vertebral levels. Your cervical region is your neck, your thoracic region is your thorax, and then you have your lumbar region, which is your lumbar spine, and then your sacral region, or your sacral nerves. All of the spinal nerves are mixed, so they're going to carry both afferent and efferent information. The spinal nerve cell bodies are located within the gray matter of the cord. The collection of the nerve fibers in the inferior vertebral tunnel is called the cauda equini. Now, I mentioned that the cord itself does not go the whole way down and stops about L1 or L2, okay? So this area right here, if you're looking at this slide, but also this picture is on page 227. You can see where it tapers, the cord itself tapers right around L1-ish, okay? And then it's gonna have like these little fibers come off in like a horsetail, okay? Which is why it's called cauda equini, okay? The fibers will then lead out to different regions of the lower portion of the body. The spinal nerve fibers that exit the vertebral column, they're only about 1.5 inches long, and then they'll divide into what's called a dorsal ramus or a ventral ramus, depending on how they're, after they come out. And we walked through that a little bit when we were looking at the spinal cord, like how the parts join together and actually then form a spinal nerve. After it makes the spinal nerve, it has to be directed either to the front side of the body or the back side of the body. That's all it's saying there. And here's a picture of that. And this is also in your book on page 227. So the ventral rami that come out of the thoracic region, they're going to become the intercostal nerves that will help with breathing and rib expansion, etc. The ventral rami of a spinal nerve that would exit in the cervical or lumbar regions are going to form what's called a plexus. And these are concentrations of like a big giant highway of nerves. We have a nerve root plexus in multiple areas of our body. So we have a cervical plexus, a brachial plexus, a lumbar plexus, and a sacral plexus. And you can see there's a chart, again, page 228. You can see a little bit of it on page 229 in the pictures when we talk about a plexus. It's going to be this. After the nerve roots exit the spinal cord, we have another like meeting point or conglomeration before it has to like go out into the periphery to serve whatever area it's serving. So I think it's relevant to just note here that if an area of a plexus gets damaged, if the nerves get damaged, there can be impacts below the nerve roots. I didn't mention this out loud, but this is kind of the point of paralysis. We understand, and we've already mentioned that, you know, neurons don't have centrioles. They can't divide themselves. So if a cell gets damaged, it's not replaceable. Is it impossible? No, absolutely not. Your body has an ability to make new highways in so many areas, in so many different ways. But this one is a little bit tougher and takes a little bit of time. So if we get damage in an area where there's a plexus to our nervous system, there can be downstream impacts depending on what plexus is involved. Okay, so when we go into then the autonomic nervous system a little bit more, remember it's broken down into sympathetic and parasympathetic nervous systems. The somatic nervous system, we can say somatic nervous system, and the autonomic or involuntary nervous system. The somatic nervous system will send impulses to activate skeletal muscles. The autonomic nervous system is programmed by the CNS to control the heart, smooth muscles, and the glands. Autonomic cell bodies that originate within the spinal cord will reside in the lateral horn of the gray matter. Myelinated axons of a first order neuron, okay, one that's going to link with another one, will terminate at a synapse with a second order neuron in what we call a ganglion. Now, when we were looking at that picture of the spinal cord a few slides up, and we saw it looked like a bulb, right? It's the dorsal root ganglion. This is where we have a junction point of neurons. We already talked through what a presynaptic and postsynaptic neuron are. Now, when we're referencing this and we understand what a ganglion is, and we have this junction point of multiple axons with other cell bodies, we have what's called a preganglionic neuron. Hope that makes sense in the language, and then a postganglionic neuron. Within them, the sympathetic nervous system, I already mentioned, fight or flight responses, we're going to notice sympathetic nerves having their direction within the thoracolumbar region. That should make sense. If we are determining whether we're running or fighting from a tiger, it doesn't matter. It's going to take some type of activation in our bodies, either to run away or to stay and fight. It's going to need large amounts of muscle control, increased respiration, heart rate increasing, stuff like that. So the relevancy here is in those ganglion, we have the connection point to get some of this stuff stimulated, and those ganglion will line your thoracic along the spinal column on the posterior region, okay, along your rib cage. In these nerves, we're going to see the formation and secretion of acetylcholine to stimulate those paravertebral ganglia I just mentioned. Okay, those sympathetic chain ganglia that are going to be lined up on the posterior aspect really of your thoracic cage in order to be able to inspire pretty rapidly a change in heart rate, breathing rate, etc. Okay, it's going to be up regulated or uptoned. They're going to be acetylcholine will be involved. Okay, and norepinephrine. The norepinephrine will be released by the postganglionic neurons to have an impact on the effector organ or cell. Now, when we talk parasympathetic nerves, it has a function in regulating more, that's your, like I said, your wine and dine response. So we're talking something that when it's in balance or high tone, it's going to help with digestion, urination, immune system function, and sexual responses. But if the sympathetic nervous system is hypertoned and you're in chronic stress and you're always fighting a tiger, this guy's not going to get an opportunity to do what it needs to do. And having said that, you have both sympathetic and parasympathetic nervous system control happening at the same time on particular organs. So it's they're dancing together and talking together. Now, within the parasympathetic nervous system, the preganglionic neurons, the ones before we get to the chain ganglia, right, or any ganglia, this is called the craniosacral division. The activation of the neurons releases acetylcholine. So the activation of both preganglionic and postganglionic neurons in the parasympathetic system will trigger the release of this acetylcholine. And it brings us out of fight or flight. So we need it to be working right alongside sympathetic tone. Okay, so let's just walk real quick through then the development of the nervous system, how it works. So neural stem cells, these are known as neural progenitor cells. We see them in the embryo, and during the first 3 through 8 weeks in development. This is when we're going to see the highest production in nervous system tissue in a developing fetus. When we are developing, and this is pretty cool, okay, there are cells, neuroglial supporting cells that are going to escort neurons to the right place. From week 9 through birth, we see that gyri and Salk-Gear form. We're going to see the fissures created in the separation of the hemispheres as well. Now, some structural changes that we notice, of course, are going to happen throughout infancy, childhood, and adolescence. As we develop into bigger humans, we have more myelination occur. And then we'll have our reflex arcs occur as well. The Babkin reflex, this is when we would apply pressure to the baby's palm, which would cause the opening of the mouth and the closing of the eyes. It will disappear between months 2 and 4. The Landau reflex, this will occur when suspending an infant horizontally in prone position, which will flex, or when flexing the head and the trunk will also cause the legs to flex. And this will disappear around 3 months of age. Well, between 3 months and somewhere between 1 year and 2. So this indicates to us the development of the structure of not only mostly the cord and the nerve roots. As we enter and as we age, okay, we're developing more of these, and they're developing differently. The brain reaches full size at about age 25. Beyond 25, and then this kind of goes across the board, okay? This is really when we like build our bodies up to about age 25, and then it starts to kind of take some backslide. Brain function will tend to decline as we age. Short-term memory, verbal abilities might be decreased, and intellectual capacity can be decreased. Impulses can slow. Exercise, once again, putting a plug in for movement, can slow all of that down. Now, one thing I want to put in here that's really relevant, okay, the human brain grows in response to stimulus, which is why as we're seeing changes from infancy, childhood, and adolescence, we as a human will grow from those reflexes that we mentioned from the first couple months of life into the first couple years of life into something of bigger cognition, because it's like we had time to integrate information here. The brain gets fed, sort of, not biochemically, but through stimulus. If it maintains stimulus, it works better. So we've heard maybe like infants or babies that aren't touched a lot, okay, their brains don't tend to grow or enhance quite as much. At any rate, that's kind of where that's coming from. Not even kind of. Okay, I think this is our last section of this chapter. I might be wrong. Nope, this is it. Okay, so this is talking about brain injury. Now, I may post a video from a guy that did a TED Talk. I think he's pretty brilliant on brain damage and therapeutic interventions, because there is this concept that nothing can be done, but there is. Okay, you can nourish brain tissue against stimulus. You can work on actually healing it. As far as regeneration of it, there's a little box on page 230 you can check out for nerve regeneration, where it talks about, how it's difficult to get nerve regeneration, but it's not impossible. Okay, so regardless of what what was reported, it's not impossible, again, due to just really the magic of the body and how it can do things that we intended to do. At any rate, when we're talking about brain injury and what can be done, the interventions I would say that are common, there aren't that many when we have brain injury, but there are things out there and other therapies that can be incorporated that can really, really help. So when we're talking about a traumatic brain injury, someone may lose consciousness. The symptoms may include headache, nausea, vomiting, convulsions, seizures, watching for pupil dilation of one or both, loss of coordination, confusion, agitation. And this can come, you don't have to hit your head. Okay, you can be in a car accident, not hit your head, have your brain have a concussive force against or in a cranial vault, and have a traumatic brain injury that's not going to be diagnosable on any diagnostic imaging, or maybe it is, okay? But generally, if you don't hit your head, you're not going to look for anything. It doesn't mean it's not there. Let me put this in here as well. Emotional traumas and stresses are also under this classification of traumatic brain injury. Can an emotional trauma damage your brain? Absolutely. This could be mental or emotional abuse type stuff. Okay. Absolutely. Damages brain tissue. If you understand how the chronic stress principle works, that's why. So traumatic brain injury from in the moderate to severe category. Obviously it gets a little bit more intense and severe with symptomatology, and you'd require immediate care. This is if you lose oxygen to the brain or blood pressure to the brain, which the drop in blood pressure would reduce oxygen, and energy to the brain. This could be for a million reasons. Okay. This could lead to coma or death. So in this is in your book on page 234, and in regards to this slide, Phineas Gage, so who had an iron rod blasted through his skull. The damage done to a brain, and just because you get hit in the brain or something obviously poked through it doesn't necessarily equate to death, as we're seeing, and this is a really severe and intense case. But you know, it may not kill you right away. It may not kill you at all. It's going to depend on what brain centers are damaged, really. This is kind of the principle too. If someone gets shot, but it doesn't penetrate certain parts of the brain or doesn't penetrate a particular tissue, you can still survive in many cases. So when we have traumatic brain injury, again, there are rehabilitation programs. When you have a brain injury, your personality does change. Okay, there's definitely this can, and again, let's talk about what's a traumatic brain injury. What's the origin? It's not always like a rod through the head. It's not always, you know, a concussive force. Maybe you're playing football. Okay, a concussion is a traumatic brain injury. You don't have to be in a car accident where you hit your head. You could have a brain tumor. You could have had brain surgery. You could have had mental emotional abuse and trauma, which created chronic stress, anxiety, and PTSD. Are these rehabilitative? Yes. Or rehabilitatable? Yes. Okay, cerebral palsy. This is a group of nervous system disorders that's caused by brain by damage to the brain before or during birth, we classify it as a congenital defect. It will have abnormal shape or structure, damage to cells and tissue. This can be contributed to by certain maternal diseases during pregnancy. Symptoms of CP involve motor function impairment, can include hearing or vision loss, and cognitive impairment as well. Spastic CP is the most common that we may think of when we think of cerebral palsy. It's very tight muscles and joints, and they may or may not be ambulatory. So far, we don't have a cure, quote unquote. It is an epigenetic thing. So there can be surgical interventions for something like this, maybe to help with some of the muscle and joint stuff primarily. Now, spinal cord injuries. This is kind of a big deal. If you have a spinal cord injury in the area between C1 and C3, this is usually fatal. This has to do with the nerve root, or a nerve root, or many nerve roots that come out of the spine in that area that will supply the diaphragm. So your breathing is shut off right away. This is the principle of hanging someone, by the way, okay, breaking the neck in this area of the cord. C1 through C4 damage, this is what we call quadriplegia. Everything below the neck is disrupted in function as far as movement. C5 through C7, this is complete paralysis of the lower extremities, partial loss of the function of the trunk of the upper extremities. When we talk T1 through L5, we're talking paraplegia. This is the loss of the function of the trunk and legs. If someone has gone through a trauma, immobilization is super relevant and called for in this event, just in case there is a fracture. We don't want to sever the cord. Now they are doing transplants of prosthetics. I think this is kind of cool information on how we can assist with spinal cord injuries and other things where they get again, transplants for something that will inspire the delivery of motion and such. Okay, we talked about the meninges. This is where meningitis comes in relevance. This is the inflammation of the meninges surrounding either the brain and or the spinal cord. The swelling of these membranes is what will create the problem. They are caused by infections. So you can have viral meningitis and bacterial meningitis or a fungal meningitis. And this is where you want to seek immediate attention. One is treatable and one is not. Bacterial meningitis is more serious than the viral. And we can treat it. So that's kind of cool if we can get the medication in there. MS, we talked about Schwann cells and the oligodendrocytes producing the myelin sheath. In multiple sclerosis, or MS, this is an autoimmune disease where these specific cells are attacked, whereby they cannot produce the myelin. So then we're going to have symptoms that will occur will be loss of balance and coordination, double vision, maybe problems with urination, defecation, sexual function, etc. Here it says no known cure also. However, if you know anyone with MS, and this won't work for everybody, just like there's, nothing that works for every one person. There is a medical practitioner. Her name is Dr. Terry Walls. She healed herself of her MS. She has been ambulatory for quite some time because she healed it with diet. And what she was putting in her body, she gave her body a chance to heal, and she did really well. She did a great job. Obviously, she was non-ambulatory and then went to ambulatory. Epilepsy, this is seizure disorder. Depending on the area of the brain that's impacted, will deliver an awareness of what kind, or, deliver whatever kind of epilepsy is supposed to be there. For the most part, you can control it by medication. Parkinson's disease, this is a later in life disorder, and this comes from damage to a particular brain center that's responsible for coordinating and initiating movements. It says men and women affected equally. However, I want to say that's a little less than accurate. I do feel it's more predominant in men. It will deliver impairment of autonomic as well as cognitive functions. One thing I believe I've said before also, when we see diseases or disorders that have a difference in presentation as far as age or gender, we're talking hormone changes in both cases. Okay, Huntington's disease, this one's pretty rare, also called Huntington's chorea. Chorea, I guess that's how you pronounce it. This is a genetic mutation that also shows up a little bit later in life. It is rare. If you know you have a family with it in your line, you watch for it. The age of onset and rate of progression may vary, and it will create neuromuscular issues, intellectual impairments, and potentially psychiatric issues. What we're doing now with it, again, modifying it with medications, as well as trying to genetically engineer some things to change it. One that's a lot more common, dementia. Alzheimer's, by the way, is under the umbrella of dementia. Okay, that came directly from a neuropsychiatrist, I guess. So I'm very familiar with Alzheimer's disease. When you have the loss of function on 2 or more areas of cognition, usually happens after age 60, and there's generally a disruption of blood supply to the brain. So they think tons of theories about this, though, not super sure. And there are multiple theories of causes. You can have early onset Alzheimer's, which is before age 60, and it worsens quickly. And they're theorizing genetic predisposition. Well, that's likely. Okay. One thing, we haven't talked about it when we're talking about any disease, also, we inherit our mother's mitochondrial DNA, which is different than our cellular DNA. Okay, so if we have a disease that has any correlation to mitochondrial dysfunction, and our mom's had it, then we're going to be predisposed. So late onset Alzheimer's, most common. It will have early symptoms, and probably about 30 to 40 years prior to its actual presentation, you'll have a traumatic event. Whatever happens very far prior to having this happen. Again, multiple theories of where it begins. Really, from my experience in the diagnostics of Alzheimer's, it's hard to say actually what it is until you get an autopsy. They can do PET scans, which can be functional, trying to look at the placement of any sclerosing or plaquing in the brain or any areas of dysfunction. And it just progresses. It's just like it all starts to shut down. Okay, so we'll add another 2 questions for your little quiz or bonus, whatever I decide to make it into here. I will add 2 more questions to it from this medical terminology portion. Okay. And I'll see you in the next video.